because as far as electronegativity goes, we would say oxygen is more electronegative than carbon, so we'd expect the polarity of the bond to be pulled, electrons being pulled toward the oxygen. Now, because of the formal charges, though, the electrons are arranged in a way that the carbon is negative because of the extra electrons, and the oxygen is positive because of the efficiency of electrons. So it's not quite as big of a difference as we would normally expect in a polar molecule, but carbon monoxide is polar. Now, polar means it's got a negative end and a positive end. Now, contrary to what the electronegativities tell you, the formal charges actually mean carbon monoxide is a little bit negative on the carbon end, a little bit positive on the oxygen end. But that separation of charge is important in terms of physical properties. Now, we don't see a real big difference here, but we do see a difference, and that's sort of a distinction we are going to want to build on. Now, for these molecules, they're both gases, but a really good way to think about the strength of intermolecular interactions is boiling points. So a boiling point would require the liquid to change phase and become the gas. Liquids, the molecules are all close together, so any type of intermolecular interaction happening between molecules would be occurring in the liquid. Gases, the molecules are spread far apart. So to spread the molecules apart, we would have to break or overcome whatever type of intermolecular interaction is happening. So boiling point is going to give us a good idea of the strength of the intermolecular interactions. The boiling point of nitrogen is 100 minus 196 degrees Celsius. Now, carbon monoxide, exactly the same shape. It's a linear diatomic molecule. It's even the same mass. Right? Nitrogen is 14.01, so 14 plus 14 is 28. Carbon is 12.01. Oxygen is 16. So you add those together and you also get 28. The boiling point of carbon monoxide is minus 192 degrees Celsius. And again, that's a little difference. It's not a real polar molecule because of kind of the uneven electron distribution. But the molecule having polarity will lead to a stronger set of interactions. So because of the polar nature of CO, we see it takes a little more energy to boil the carbon monoxide from its liquid state than it does to boil nitrogen from its liquid state. Now we're going to see there are much bigger differences as we go into maybe a little more complicated structures. The second comparison, we want to compare CH4, which is methane, to water. Now again, these are going to be about the same size, but we'll start to see some really distinct differences. Now, methane, the carbon atom is the only atom in that molecule that can make more than one bond. So we'd want to put carbon in the middle, and we'd also want to connect the hydrogens to it. Now, since I know I'm connecting 4 hydrogens to the carbon, I know this is going to be a tetrahedral molecule, right? That may be an extra step you'd want to take after you draw the molecule kind of in a flat perspective, is to then realize, oh, there's 4 sets of electrons. This is really a tetrahedral. But methane looks like that. Carbon with 4 hydrogens attached to it. That satisfies the octet rule for the carbon in the middle. We get something kind of similar with water, but with only 2 hydrogens, there are some leftover electrons that end up on the oxygen. Now, this is also tetrahedral in terms of the electrons associated with the oxygen atom. There's 4 sets of electrons here, 2 bonding sets and 2 non-bonding pairs. But the way we described the molecule is as bent, like we talked about in the last video. So methane is a tetrahedral, water is bent, but tetrahedral leads to this being a nonpolar molecule. There's a slight electronegativity difference between carbon and hydrogen, but in a tetrahedral, even though the carbon may be pulling electron density a little bit from this hydrogen that's kind of pointed upward, the other 3, the carbon is pulling electron density from them, and each of those has a slight, that would be downward, this one, and these would all be slightly upward. So because the molecule shape is symmetrical, it's nonpolar. For water, that's not the case. As we talked about before, the oxygen's more electronegative. It's pulling the shared electrons in towards itself. These are polar. molecules. Now, here we'll see, similar shaped molecules, again, similar sizes, right? What is the difference in the boiling point? The boiling point of methane, you may be aware, methane is a gas at room temperature. The boiling point of methane is minus 162 degrees Celsius. So it's a gas. At very low temperatures, it transitions into a gas. And we're probably all familiar with the fact that the boiling point of water is 100 degrees Celsius, water being a liquid at room temperature. So there's a very big difference here between these two molecules. Even though, again, they're about the same shape, about the same size, the methane is held together with much weaker types of interactions than what we see for the water. Now this, of course, is partly because of the polarity. Water is a polar molecule, so in a sample of water, the molecules will interact with each other through these dipole-dipole interactions. Now there's a little more to the story, and that's why we have another example here on this page before we kind of complete the picture that we're looking at here. The third example, we're looking at a couple of similar compounds, and what I've done is replaced carbon with silicon. Silicon's right below carbon in the periodic table. So in terms of bonding, silicon and carbon, particularly in covalent compounds, so compounds with other nonmetals, very similar. So silicon is going to be in the center. It's going to have 4 bonds to the hydrogens. It's going to be a tetrahedral. Sulfur is right below oxygen, so it will also bond in a very similar fashion. It'll be in the center. There'll be 4 leftover non-bonding electrons for the sulfur. Now, up here in the middle example, we saw a very stark difference between the boiling points. For the third set of structures here, we don't see quite as big of a difference. The boiling point for silicon and 4 hydrogens, which is called silane, is minus 112 degrees Celsius. So it's a gas at room temperature, and in fact it transitions from liquid to gas, again at a very low temperature. Now, the comparison between methane and silane is something we'll get to when we talk about kind of the last couple sets of types of intermolecular interactions that occur in nonpolar materials. But the difference here between oxygen in the middle and sulfur is particularly important to recognize, because H2S, or hydrogen sulfide, is also a gas. So the boiling point is well below room temperature. It's minus 60 degrees Celsius. So within the comparison here, again, we have 2 molecules that are about the same size, about the same shape, but there's a big difference between the nonpolar molecule. So again, silane being a tetrahedron is nonpolar. Hydrogen sulfide being bent is polar. We see a big difference between the boiling points of the polar molecule and the nonpolar molecule. Now, what we don't really explain is the differences here between water and hydrogen sulfide. And what we need to watch out for, right, this type of interaction is explained by a subset of dipole-dipole interactions called hydrogen bonding. So hydrogen bonding is a type of intermolecular interaction, and I'm just going to use II here for intermolecular interaction, that occurs between small, highly electronegative atoms and hydrogen. Okay, so in order for us to have hydrogen bonding, we need to have small, highly electronegative elements, and in this case, those would only be oxygen, nitrogen, and fluorine. Anything else is either big, even if it's highly electronegative, like chlorine, or is not electronegative enough, like carbon. So if our molecule has a hydrogen attached to an oxygen, a nitrogen, or a fluorine, it could have hydrogen bonding. And hydrogen bonding looks something like this. So we used water as our example before. It was kind of out of line with the other trends. Right? We know that water has partial negative on its oxygen And then there would be partial positives on the hydrogens, the other ends of those bonds. Well, what happens in a sample of water is the other water molecules can line up in a way that there's an interaction between the partial negatives and the partial positives. So you use kind of a dotted line to indicate this interaction. That's our hydrogen bonding interaction. Ooh, I added an extra letter there. Right? Now, because oxygen is so electronegative and it's so small, it's got a fair negative charge on it in the polar molecule. Hydrogen's got a fair positive charge on it. So there's a charge component here as well. That's where the highly electronegative comes in. But distance is important here as well. The oxygen, nitrogen, or fluorine, they're pretty small atoms as well in these molecules. So they can get really close to the hydrogen in a way that a larger atom cannot. And as a result, if we have this type of interaction, hydrogen bonding, this can be about 3 times stronger than other dipole-dipole interactions. And I'm going to use an abbreviation for dipole-dipole here, just DD interactions.